Greetings, I am Janil Kalathiya and today I will be presenting my directed research project on value stream mapping for slab cycle monitoring and reducing time of slab cycle. This study is guided by Mr. Manish Dave and is carried out as a part of the MTech Construction Engineering and Management program at CEPT University. The main idea of this research is to understand how value stream mapping or VSM can be used in a real life construction site condition. Usually, slab cycle monitoring is done by comparing planned and actual dates. That tells us whether there is a delay, but it does not clearly explain why the delay happened or occurred. So, in this study, I have tried to go one step deeper. I have applied VSM to analyze the slab cycle of pour 1 of the second basement roof slab, having an area of 815.11 square meters. The study focuses on three main activities: shuttering, reinforcement, and casting. The aim is to identify where time is being used productively, where time is being lost, and how the slab cycle duration can be reduced through a proposed future state. This is the overall flow of my presentation. I will begin with the introduction and background, where I will explain why this topic was selected and what problem the study addresses. After that, I will briefly explain the literature review covering lean construction, VSM, waste classification, and takt time. Then, I will discuss the research methodology, including the case study design and the analysis stages followed in this research. After that, I will explain the data collection part, where I will talk about the selected pour, quantity data, and the type of information recorded. Then I will move to the main analysis, including planned versus actual comparison, takt time analysis, current state, VSM, VA, non-value added but necessary, non-value added classifications, waste analysis, and productivity analysis. After that, I will explain the future state VSM and the lean tools proposed for improvement. Finally, I will conclude with the current versus future comparison, major findings, practical recommendations, limitations, and future scope. So, to begin with the background, time is one of the most important control parameters in high rise residential construction. In high rise projects, slab work is repetitive. One slab cycle is followed by the next slab cycle. So, if one slab cycle is delayed, the impact does not remain limited to that one cycle. It can affect labor planning, material movement, equipment use, site coordination, and even the starting condition of the next work stage. In normal site practice, we usually monitor progress through planned versus actual comparison. This is useful because it tells us whether an activity is delayed, on time, or ahead of schedule. But the limitation is that it does not explain the internal reasons for delay. For example, if shuttering is delayed, planned versus actual tracking will show that the shuttering activity took more time, but it will not clearly show whether the reason was idle manpower, late material movement, rework, poor handover, delayed instruction, or an inspection readiness. That is why I selected value stream mapping for this study. VSM helps to analyze the process as a flow. It separates time into value added time, necessary non value added time, and non value added time. It also helps in preparing current state map and proposed future state map. So the selected study unit is pour 1 of the second basement roof slab with an area of 815.11 square meters, and the focus is on shuttering, reinforcement, and casting. The problem statement The main problem statement of this research is that planned versus actual monitoring shows when an activity is delayed, but it does not explain why it is delayed. In slab cycle work, not, the delay may not be only because the actual physical work took more time. It may be because of supporting issues like idle manpower, material handling, rework, delayed instruction, inspection delay, or weak handover between activities. So, there is a need for a process-based method that can identify the internal reasons for time loss. The aim of this research is to apply value stream mapping for monitoring and analyzing the slab cycle of pour 1 of the second basement roof slab. The study focuses on identifying value added, non-value added time in shuttering, reinforcement, and casting, then proposing improvements to reduce slab cycle duration. The objectives follow this aim step by step. First, I studied the existing slab cycle process. Then I defined the VSM boundary for the selected activities. After that, I collected planned and actual time data. Then, the time was classified into VA, necessary NVA, and NVA categories. After that, waste types, downtime, and occurrences were identified. Actual performance was compared with planned or tag time. Productivity was analyzed using quantity and time data. Finally, the current state value stream mapping and future state value stream mapping were prepared. So, the study is not only about identifying delay, it is about understanding the reason behind delay and developing a future state improvement proposal. Scope of study. This slide shows the scope of the study. The selected pore area is 815.11 square meters. The study is limited to one pore, which is pore 1 and second basement roof slab. The VSM boundary includes only three activities: shuttering, reinforcement, and casting. These three activities were selected because they are the main activities in the selected slab cycle process and they are directly connected to each other. Shuttering prepares the work front, reinforcement follows after shuttering readiness, and casting depends on both shuttering and reinforcement completion for the slab. For the verticals, reinforcement prepares the work front, shuttering follows after reinforcement readiness, and casting depends on both of the activities. The study includes planned versus actual comparison, classification of the waste, downtime and waste occurrence analysis, tech time comparison, and productivity analysis. At the same time, some areas are excluded: cost analysis, safety analysis, structural design analysis, comparison of shuttering system, and other slab pores are not included. This was done to keep the study focused and detailed rather than making it too broad. This slide explains the main concept used from literature. The first concept is the difference between conventional monitoring and VSM based monitoring. Conventional monitoring mainly focuses on planned versus actual progress. It tells us whether work is delayed or not. But VSM based monitoring focuses on process flow and time use. It can show the current state, identify waste, classify time, and support future state improvement. The second concept is VA, necessary NVA, and NVA. VA, or value added time, is time that directly contributes to the completion of the slab. In this study, examples include shuttering erection, reinforcement fixing, and concrete placement. For NNVA, that is necessary non-value added time, includes support activities that may not directly transform the work but are still required under current site conditions. For example, checking, staging, or inspection readiness. NVA or non-value added time is avoidable waste. This includes waiting, idle manpower, rework, break delay, and unnecessary movement. The third concept is takt time. In this study, planned time is treated as the expected work rhythm. The takt gap is calculated as actual time minus planned time. If the value is positive, the activity is delayed compared to the planned rhythm. The fourth concept is value stream mapping in construction. VSM helps to map material flow, information flow, current state conditions, and future state improvements. So, the literature supports the method used in this study. This slide shows the research methodology. The study follows a case study based applied research design. This is suitable because the research is based on a real life site process and real data. There are 9 main stages in the methodology. First is planned versus actual comparison. This gives a basic understanding of schedule variance. Second is takt time analysis. This shows which activity is not matching the planned rhythm. Third is current state VSM, which maps the existing process. Fourth is value adding, non-value adding but necessary, and non-value adding classification. This helps to understand how time is actually being used. Fifth is waste occurrence analysis, where the number of times each waste occurred is identified. Sixth is downtime analysis, where the actual time lost due to the waste is calculated. Seventh is productivity analysis, where output per hour is calculated. Eighth is current versus future comparison. And ninth is preparation of the future state VSM, where improvement actions are proposed. So, this methodology combines schedule monitoring, value stream mapping, waste analysis, takt analysis, and productivity analysis in one framework. So, coming on to data collection. This slide explains the data collected for the selected tool. The total quantity of reinforcement considered is 46,213 kilograms. The total shuttering quantity is 2,148.89 square meters. The total casting quantity is 357.09 cubic meters. These quantities are important because they help connect time with actual work output. Without quantity data, productivity analysis would not be possible. The data fields recorded include activity and sub-activity, start and end time, duration in hours, manpower assigned, quantity of work, classification of the activities, downtime or waiting time, waste type, and remarks. Site photographs were also used to support the observations. These photographs show the actual site activities such as reinforcement, shuttering, and de-shuttering. So, the data collection was not only based on time values, it also included quantity, manpower, waste reason, and site observations. Planned versus actual duration analysis. This slide shows the planned versus actual duration analysis. This is the first level of monitoring. For vertical reinforcement, the planned duration was 8 days, while actual duration was 12 days. So there was a delay of 4 days. For vertical shuttering, the planned duration was 20 days, while actual duration was 29 days. So there was a delay of 9 days. This is the highest delay in the tracking level analysis. For vertical casting, the planned duration was 18 days, while the actual duration was 22 days. So again, there was a delay of 4 days. For horizontal shuttering and horizontal reinforcement, the work was completed ahead of planned time. However, horizontal casting was delayed by 3 days. The key finding from this slide is that vertical shuttering had the highest delay. The takt time analysis also confirms this because vertical shuttering had the highest takt gap of plus 99 hours. Another important point is that horizontal reinforcement was completed earlier, but horizontal casting was still delayed. This shows that even if one activity is completed early, the next activity may still be affected by other issues such as readiness, coordination, or instruction delay, or any issues or disputes occurred on site. So planned versus actual analysis is useful, but it is not enough. We need VSM to understand why these delays occurred. Current state VSM summary. This slide shows the major current state VSM numbers. The total elapsed cycle time is 574.97 hours. The total downtime or waiting or delay is 291.25 hours. The total activity classified time is 696.50 hours. Here, it is important to understand that elapsed cycle time and activity classified time are different. Elapsed cycle time represents the overall process flow duration. Activity classified time represents the total time classified under shuttering, reinforcement, and casting. Since some activities and delays overlap on site, these two values are not treated as the same. Now, out of the activity classified time, 400 hours are value added. This is 57.43%. 98 hours are necessary non-value added. This is 14.07%. And 198.5 hours are non-value added. This is 28.5%. This is one of the most important findings because almost one third of the activity classified time is avoidable waste. So the improvement potential is mainly in reducing NVA and part of necessary but non-value added time, which is 98 hours for the necessary non-value added time. This slide shows the current state value stream mapping flowchart. The flowchart represents the existing slab cycle process. It includes information flow, material, or workflow. and time classification for the selected activities. The three main activities are shuttering, reinforcement, and casting. The map also includes the overall elapsed cycle time of 574.97 hours and total downtime of 291.25 hours. The importance of this map is that it makes the process visible. Instead of looking at delay only as a number, we can see the activity sequence where time is consumed and where waste is located. This current state map becomes the base of developing the future state map. So the logic is first understand the current process, then identify the waste, and then propose improvements. This slide breaks down VA, necessary NVA, and NVA activity wise. For reinforcement, the total time is 257.75 hours. Out of this, VA is 126.75 hours. Necessary NVA is 43 hours and NVA is 88 hours. The NVA share is 34.14%, which is the highest percentage among the three activities. For shuttering, total time is 344 hours. VA is 199 hours. Necessary NVA is 47.50 hours and NVA is 97.50 hours. So, shuttering has the highest total activity time and the highest NVA in absolute hours. For casting, total time is 94.75 hours. VA is 74.2425 hours. Necessary NVA is 7.50 hours and NVA is 13 hours. Casting has the lowest NVA among the three activities. From this, two major points can be concluded. First, shuttering is the biggest waste contributor in terms of total NVA hours. Second, reinforcement is the most waste intensive activity in percentage terms. Together, shuttering and reinforcement account for 185.50 hours out of the total 198.50 hours of NVA. So, the future state improvement should mainly target shuttering and reinforcement. Waste occurrence and time loss analysis. The slide shows waste occurrence and time loss. The total number of waste occurrences is 342 and the total time lost is 291.25 hours. The most frequent waste is non-working time or break delay with 142 occurrences and 71 hours lost. Transportation of material handling occurred 49 times and caused 31 hours of loss. Motion of preparation housekeeping occurred 41 times and caused 22.5 hours of loss. Waiting due to instruction or approval occurred 39 times but caused only 9.75 hours of loss. The most important point here is waiting due to idle manpower. It occurs only 26 times but caused the highest time loss of 93.25 hours. So, this slide shows that frequency and severity are not the same. A waste category may occur frequently but causes smaller time loss. Another waste category may occur fewer times but creates a much larger time loss. Therefore, improvement should not be based only on the number of occurrences. It should also consider the time lost. This is why idle manpower becomes the most critical delay cause, even though it is not the most frequent. Top delay causes, and productivity analysis. This slide summarizes the top delay causes based on time loss. The first and highest delay cause is waiting due to idle manpower with 93.25 hours. The second is non-working time or break delay with 71 hours. The third is defects or rework with 37 hours. The fourth is transportation or material handling with 31 hours. The fifth is motion or preparation housekeeping with 22.5 hours. These causes show that slab cycle delay is not only because of slow work execution, it is also because of readiness, coordination, material flow, rework, and labor utilization issues. The slide also shows current state productivity for reinforcement productivity is 179.29 kg per hour. Shuttering productivity is 6.25 square meters per hour. Casting productivity is 3.77 cubic meters per hour. For shuttering productivity, it is 6.25 square meters per day. These values help connect time loss with output. When time is reduced in the future state, productivity improves because the same quantity is completed in less time. Future state VSM, basis and lean tools. This slide shows the basis for the future state VSM. The future state proposal is prepared based on the problems identified in the current state. The main problems are idle manpower, break related delay, rework, material handling, poor workfront readiness, instruction delay, and weak handover. To address these problems, lean tools are proposed. Workfront readiness is used to reduce idle manpower. Look ahead planning is used to prepare labor material and equipment before the activity starts. Daily coordination meetings are used to reduce instruction and decision delays. Material staging is used to reduce repeated material shifting. 5S is used to improve workplace organization. Handover checklist is used to reduce delay between shuttering reinforcement and casting. Quality at source is used to reduce rework. Pre-pour checklist is used to ensure casting readiness. And controlled restart after breaks is used to reduce non-working time after breaks, so each lean tool is linked to a problem identified in the current state analysis. This slide explains the improvement strategies separately for shuttering, reinforcement, and casting. For shuttering, the current state time is 344 hours and the future state time is 261.23 hours. The expected saving is 82.77 hours or 24.06%. The main shuttering problems were repeated material movement, poor tool arrangement, rework in fixing or alignment, and delay in handing over the work front to reinforcement. The proposed actions are mainly material staging, 5S, quality at source checks, and handover checklist. For reinforcement, the current state time is 257.75 hours and the future state time is 183.10 hours. The expected saving is 74.65 hours or 28.96 hours. 96%. The main issues were labor waiting for shuttering work front, steel not being fully ready, rework in fixing, and instruction or clarification delay. The proposed actions are workfront readiness, look ahead planning, material staging, quality at source, and daily coordination meetings. For casting, current state time is 94.75 hours and future state time is 78.63 hours. The expected savings is 16.12 hours or 17.02%. The main casting issues were delay before post start, uncertainty in equipment or resources, and restart delay after breaks. The proposed actions are pre-pour checklist, resource readiness check, and controlled restart after breaks. So the future state strategy is activity specific. It is not one general solution for all activities. This slide shows the future state VSM flowchart. The future state represents the proposed improved processes. It is important to note that the future state is not yet actual achieved performance. It is a proposed condition based on current state waste reduction. In the future state, the elapsed cycle time becomes 406.67 hours. Downtime reduces to 122.95 hours. The map shows how lean tools are applied around the process. For example, material staging and fires are applied to reduce material handling and motion. Workfront readiness and look-ahead plannings are applied to reduce idle manpower. Handover checklist and daily coordination are used to reduce transition and instruction delays. Pre-pour checklist and resource readiness are applied before casting. The future state map shows that improvement is achieved by reducing avoidable waste, not by reducing the actual value added. This is the main result slide of the presentation. The current elapsed cycle time is 574.97 hours. The future elapsed cycle time is 406.67 hours. So the total time saving is 168.30 hours, which gives us 29.27% of reduction. Downtime reduces from 291.25 hours to 122.95 hours. This means a reduction of 168.30 hours in downtime, waiting and delay. Activity classified time reduces from 696.50 hours to 522.96 hours, giving a saving of 173.54 hours or 24.91%. The time classification comparison is also important. VA time remains unchanged at 400 hours. This is because the actual productive work is still required. Necessary but non-value added time reduces from 98 hours to 57.70 hours. NVA time reduces from 198.50 hours to 65.26 hours. So the biggest reduction in NVA time, which reduces by 133.24 hours. This proves that the future state improvement is mainly waste reduction, not reduction of required productive work. Activity wise and productivity improvement. This slide explains the improvement activity wise and productivity wise. In activity wise time comparison, reinforcement reduces from 257.75 hours to 183.10 hours, giving a reduction of 74.65 hours or 28.96%. Shuttering reduces from 344 hours to 261.23 hours, giving a reduction of 82.77 hours or 24.06%. Casting reduces from 94.75 hours to 78.63 hours, giving a reduction of 16.12 hours or 17.02%. The total activity classified time reduces from 696.50 hours to 522.96 hours. Now, because the same quantity is completed in less time, productivity increases. Reinforcement productivity improves from 179.29 kg per hour to 252.39 kg, which is 40.77% improvement. Shuttering productivity improves from 6.25 square meters to 8.23 square meters, which is 31.68% improvement. Casting productivity improves from 3.77 cubic meters to 4.54 cubic meters, which is 20.51% improvement. So the future state improves both time performance and productivity. Major findings. This slide summarizes the major findings. The current elapsed cycle time is 574.97 hours with 291.25 hours of downtime or delay. Reinforcement had the highest NVA share, which was 34.14%. Shuttering had the highest NVA hours, which was 97.50 hours. The highest time loss waste was waiting due to idle manpower, 93.25 hours. Practical recommendations and future scope. This slide represents the recommendations and future scope. The first recommendation is daily workfront readiness before labor is deployed. The site team should confirm that the workfront is ready. The second recommendation is daily coordination meetings. This should be short meetings before work starts to reduce instruction delays. The third recommendation is material staging. Material should be placed near the work front before the activity starts. The fourth recommendation is a handover checklist between shuttering reinforcement and casting. The fifth recommendation is quality at source. Checks should be done during execution as that so that the rework can be reduced. The sixth recommendation is a pre-pour checklist before casting to confirm concrete supply, labor, pump vibrator, and inspection readiness. The seventh recommendation is monitoring restart time after breaks. And the eighth recommendation is weekly review of downtime data. The contribution of this study is that it combines planned time, actual time, takt time, VA, necessary NVA, NVA classification, waste occurrences, time loss, and productivity into one slab cycle analysis. For future scope, the same method can be applied to multiple slab pours. The proposed future step can be validated on this next slab cycle. Cost analysis can be added, and the method can be extended to other structural elements. The main limitation is that this study is limited to one pour, and the future state is proposed not yet implemented. To conclude this study, this study shows that slab cycle delay should not be seen only as a scheduling issue, it is also a process flow issue. VSM helped identify where time was used productively, where waste occurred, and what improvements can reduce the slab cycle duration. The key results is a possible 29.27% reduction in elapsed cycle time equal to 168.30 hours saved. The study also shows a reduction of 133.24 hours of NVA time and productivity improvement up to 40.77%. Therefore, VSM can be considered a useful method for slab cycle monitoring and time reduction in high-rise residential construction. So, to summarize, this study applied value stream mapping to the slab cycle of pour 1 and second basement of roof slab. The selected activities were shuttering, reinforcement, and casting. The main reason for using VSM was that planned versus actual monitoring shows delays but does not explain the internal reason for time loss. The current state analysis showed an elapsed cycle time of 574.97 hours and downtime of 291.25 hours. Out of 696.50 activity classified as 198.50 hours were non-value added. The main waste causes were idle manpower, break-related delay, rework and material handling. A future state was proposed using lean tools such as workfront readiness, material staging, 5S, handover checklist, daily coordination, quality at source, pre-pour checklist and control restart after breaks. The future state reduces the life cycle time to 406.67 hours, giving a reduction of 168.30 hours or to 29.27%. The main conclusion is that VSM improves life cycle monitoring by identifying not only delay but also the reason and location of time loss. Thank you.